So Canny Edge Detector. So before discussing Canny Edge Detector, the algorithm, we should know about the features of Canny Edge Detector. So here, first of all, the edges are localized. That is, in an image, we go for local edges in an area. For example, we detect these edges, each edges. There is no translation. I mean, when edges are here, it should be here in the detected image also. And it is there is less error in detection. And finally, it is only one response per edge. That is, for in an image, we have such kind of structure. So when you go from here to end, this being uniformly colored, so you go from here to here, you have this one edge, and then you have another edge here. So it is believed that for 1 pixel thick image, we should have a single line. So having said all that, let's go into the algorithm. So we have step 1. For given image I, x, y, we smooth it using a Gaussian filter to get I prime x, y. Now what we do is we filter it using Sobel filter for x and y both. So for example, let's Sobel operator for direction x, I prime x, y is equals to, say, gx, then sy convoluted with I prime x, y is equals to gy, and m is equals to under root gx square plus gy square, and alpha is equals to tan inverse gy by gx. So what we have done is we have removed the noise using this Gaussian filter. After that, we detect the edges both in so we take partial derivative in x direction, so this Sobel operator sx, and in y direction Sobel operator sy. Then we calculate the magnitude of the edge using this, and then we calculate this angle. For example, in an image, if this is the edge, here we have this direction, we take partial derivative in this direction, and we calculate find out the angle of the edge through this magnitude, and we also find out the strength, the intensity difference in the partial derivative in both directions, and we take the magnitude. Now having said all that, we go to the step 2, that is non-maximal suppression. What we do it in this is we verify that the edges are strong. For example, we have this point detected as an edge in the previous step, so we take all its 8 neighbors, and we divide it into sectors, all the points. For example, let's say last time we got alpha is equals to 103 degree. So here, starting from this x direction, where is 103 degree? If this is y direction, xy, so 103 degree will fall somewhere here. this is 120 degree, this is 90, this is 90 degree, so it will fall somewhere here, right? And we have this sector, so and this region falls in this sector. So here we have this point, so here we have this point, and we take the opposite point, this one. So if m for this point is more than m for this point and this point, that means this is actually a edge point, because m value is strong enough. Otherwise it is not a actual edge point. So having said all that, we find out the we had this m, we calculate new matrix m prime, where we store the m value for all those points whose m is more than the two neighbors as mentioned here. Otherwise we in the element value will be 0 in corresponding to that pixel, m prime value will be 0. So finally we have a third step in which we do hysteresis thresholding. Hysteresis thresholding. Here in previous step we found m prime value for different edges for different points. Now we plot it. Number of pixels and this value of m prime. So for example, this m value will have very higher value is with less number of pixels, low m value is for less number of pixels. So here we detect it as divide it in 3 parts. Let the maximum, this be the maximum m value, so this is the 80% of maximum, this is 20% of maximum, and we create two matrices MNH, MNL. For those pixels whose m value is more than this 80%, corresponding to those pixels in MNH we put 1, otherwise we put 0. For MNL, for those pixels whose value is in between this 80 to 20%, in MNL we put 1 across those pixels, 0 otherwise. Now in the third step is called edge linking. Here we create a matrix E x y is equals to MNH x comma y. Fine, as we did in the we found out MNH in last slide. So, and for every point with a value 1 in this EXY, we or say in MNH XY, we look for the 8 neighbors, value of 8 neighbors in M and L. For example, if in MNH here we have 1, and these may be any value, 0, 1, whatever, 0, 0, 1, 0, 0, 0. So for each one in this image, for example, we take this one and we look for the neighbors in MNL, not in this MNH, we look for its neighbor in MNL. For example, here we have 1, and let's say its neighbors, this point may be here 0 or 1. Yeah, it will be 0 because here we have this one in MNH, So in MNL definitely it will be 0. So we are not interested in this point of MNL. Instead we are looking here at its neighbors. So for example, say here it is 1 0 1 0 0 0 0. So any point in its 8 neighbor which has one value, we mark in this EXY also as 1. So for example, say this is as EXY. So these point so here, sorry, this point and this point will be marked as 1. Again we go to this other point of MNH. Similarly we visit for every one in MNH, and corresponding to that we see MNL and we update EXY. So this was edge linking. So this is the algorithm of Canny Edge Detector. So what are its applications? Its applications are to form correspondences between two images from, for example, in slightly different angles or whatever. So we have to match. So in an image we have three areas, kind of. For example, this is a flat region, all the pixel values are equal. Here we have a straight not a straight line but a line, any curved line or whatever. So here we can have little correspondence. For example, it can vary in this direction, the value remains same, but otherwise the value changes in this direction. Or we can have an edge. Here you vary the patch in any direction, you will get a maximum mismatch. So the edge is used for making this correspondence, though it is not the best one. We preferred matching corners. So next we will see how Harris corner detector works.